Okay, so thanks for attending. Again, we're not going to have any attendance questions today because of election day. So I hope that if you have an opportunity to vote and eligible to vote, then you have gone ahead and voted or will vote today. And if now is exactly the only time that you can do that, then go ahead and do that because we're not going to have attendance, but everything's recorded. Other announcements is I mentioned that originally there was going to be homework D7, which would be the last homework, and then there'd only be 3 homeworks here. What I've done is I split that into a homework D2 and a D7. So there is a new homework where I've cut D7 in half, made it all the stuff we're kind of talking about now, and all the stuff we'll talk about starting Thursday. And all the stuff we're talking about now, you'll be prepared to do at the end of this lecture. And so that homework has been released, and you have about 2 weeks to do that. And then once that homework gets turned in, then the next homework D7 will be available. And then so because I've added a homework assignment, then I've also increased the drop policy. So now we've got 4 total homeworks, but you drop your 1 lowest. And so that's why some of you may have seen a slight uptick in your grades, because if you happen to have missed the first homework or just not do so well on the first homework, then that is has been end up being dropped. But of course, to keep that, then you have to keep doing well. And so if you didn't do as well on that first homework, then it gives you an opportunity to clean up with that on the next couple. But if you did really well on the first 3 homeworks, then maybe the 4th homework isn't as important, et cetera, et cetera. You guys know how this game works. I also am almost done, and hopefully today I'll be finished with a Canvas activity for Unit D. And then that Canvas activity, along with the Canvas activity that's already available for Unit E, will be the last Canvas activity. And so in that case, you'll know kind of all of the assignments that's from here to the end of the semester. The only other reminder I guess I'll give you is that the final for this class will be, as with all of your classes, held during the last week of classes this semester, not during the original finals week. And this is going to be a 2-stage final exam. So we will have the Tuesday of that week, we will have a final exam review. The Thursday of that week, you will do the whole lockdown browser final exam on your own, individual, 90 minutes. That will be 80% of your final exam grade. And then for the last 20% of your final exam grade, you get the exact same exam, but you don't have to do it in lockdown browser, and you are ethically free to use resources from the course Canvas page or your notes, and you are ethically free to talk to your classmates. You are still expected not to go out to websites like Chegg or Course Hero and the rest of those to seek out help. I want the help to be kind of centered, kept within the family, kept within the class, and kept within the class's notes and within the textbook for the class. But I'm trusting you to do that, and I'm trusting you to ensure that your classmates do that. At the moment, I don't plan on making that a group assignment because there's a lot of logistical issues in deciding who's in what. So at the moment, it will just be effectively a all-day open book version of the test that you took the day before. And that allows you to collaborate with everyone, whatever is convenient throughout that day. So that's the current plan. But definitely this 80-20 setup, that is kind of we're setting up for that final exam. So, and then that will be the last thing that you have to turn in for this class, because your final homework will already be in by then, and then all that will be left is waiting for us to grade that last homework assignment. So that's everything moving forward. So before I go on to the quantitative side of non-renewable resources, are there any questions about the timeline moving forward?
Is there a specific due date for honors contracts?
Oh, that's a good question. I'd say that if you have set up to do an honors contract with me, then we can discuss this over email. I feel like I don't want to be documented on, because I want to give myself time to review it. But let's say, I think that if you got it to me by the end of the original finals week, that would give me enough time to grade the honors contracts and assign the grades before grades are due a couple days later. So I would say that if you're working on an honors contract with me, you can take the normal finals week.
Okay, thank you.
Mhm. Anybody else? All right. So in a lot of your muddiest points, I've responded to all of your muddiest points. So as usual, check the responses to, I try to at least put a note in everybody's question two, their muddiest point, if not all three questions. And sometimes I'll put a note in the side comments as well. So I don't know if you get notifications about that, but if you had a muddiest point that you were interested in, then go to your muddiest point and take a look at the per question comments. And several of them said, I don't quite understand why Hotelling's rule works and stuff like that. And I didn't mean to confuse you guys, because we're going to go into that today in the quantitative stuff of how these non-renewable stuff works. I was just trying to motivate this the last time. And so that was just kind of a tip that it's coming up. So as I mentioned the last time, we view natural resource management from an economic point of view is really a question of, is capital asset, I guess maybe I'll spell that out, capital asset investment decisions. And so this word capital means that it's something you buy that you don't immediately extract any benefit from, but it allows you to get benefit from other activities. So as an example, let's say you open a restaurant, you will probably need to buy things to cook stuff on. You buy an oven, for example. But that oven, even though it was it was very expensive, but although you buy it, you don't actually get any benefit out of the oven itself in your restaurant. It was a capital investment. It was a large piece of equipment that then allows you to make food that then you can sell. And then you can sell that food, and then what you make on the sales of that food is actually the benefit that you get. So it's capital because you don't get an immediate benefit, but it ends up facilitating a longer term stream of benefits. And that's the same way we view natural resource management, is that you could try to get all of the benefit out of the natural resource immediately, but you probably would end up with a lot of deadweight loss. You'd probably end up with a more efficient way to manage that resource, is to actually conserve it into the future and be able to extract benefits off periodically, so that you've effectively turned the natural resource into a bank account that's generating interest with you. And it turns out, by Hotelling's rule, natural resources that are privately owned generate interest at exactly the same rate that the bank does. And so you manage them to sort of match what the bank is doing. So that's kind of what we're doing here. And so to kind of, and I mentioned last time that like the ultimate goal is, in general, is to maximize social welfare across the many stakeholders who benefit from natural resources in many ways. And so that message that I was trying to communicate last time may not make a lot of sense for things like oil, because we don't have a lot of ways to benefit from oil. But when we go into the next thing, where we talk about timber resources, for example, you can imagine there's lots of different ways you can benefit from a forest. You can cut all the trees down, or you can leave them up, so that people can have parks that they can enjoy in different ways, so that you get a home for wildlife, because that wildlife might provide some additional benefits, et cetera, et cetera, et cetera. So there are a bunch of different ways to manage a forest. So there's a bunch of different ways to take that capital, and it's really investment decisions. Are you going to invest all of it in timber? Are you going to invest some of it in timber? Are you going to invest some of it in recreation, some of it in species habitat? Well, how much are you going to invest? These are exactly the types of decisions you make when you say, I have $1 million to invest, and it's capital because I'm not going to actually spend that money. I'm not going to get any direct benefit from $1 million, but I'm going to put 300,000 in this stock. I'm going to put 400,000 in these bonds. I'm going to take the remaining 300,000 and I'm going to do this other thing with it. And all three of those things will give me benefits over time. I'm hoping that my capital doesn't shrink over time. That would be great if it didn't, so that I get benefits and I keep the same amount of capital. And so when we get into renewable resources, it's much more like that problem where you sort of say, how do I ensure that I can get benefits from, say, a fishery without ever worrying about the fishery collapsing? So in that case, a fishery is much more like a bank account where you're not ever actually having to worry about losing your capital. You're just able to bleed off the interest. In a non-renewable resource like oil, we do end up removing some of the resource, so we have less of it available later. But the interesting thing about that is the additional scarcity we generate later actually increases the benefits we get off of later oil we sell. And so even though the amount of principal, if we think of it in bank terms, is decreasing, it's almost as if at the bank, the interest rate increases the smaller your account gets, which is a little weird, but that's effectively, when we're thinking economically about a non-renewable resource, we are effectively turning a non-renewable resource into that bank, a bank where as your principal gets smaller, your interest gets higher. So let's see what we mean by that. So before we start talking about scarcity, then the example we might give would be for, and this is a numerical example, for like apparently unlimited oil. And so the unlimited here means there's no intertemporal trade-off. And the no intertemporal trade-off means that we don't, there's, so no worry about scarcity. So because we don't worry about time passing, then we refer to this as a static case. So static meaning not that it's, when I say not changing, what I mean is our decision-making isn't changing. Our decision-making isn't taking into account the effect of time passing. That's what I mean by static. Or a myopic case. So those are two terms that mean the same thing. And so myopic means nearsighted. So we're saying the myopic case means we are only focusing on this year, not on the effect our decisions have about next year. So saying that you can use static mathematics to solve for your optimal allocation is effectively taking a myopic stance where you're saying, I only need to see right in front of my nose. I am okay with having a nearsighted perspective in my decision making. So go ahead.
Sorry, I got a question. So
Yep.
basically you're saying static and myopic cases are both the same time window, both taking place in the same year then?
Right. So I could view this as a one period case or a single period case.
Okay.
So the time horizon is small or short. All right, so this is the naive way we do decision making, and the way we did it before, like before the midterm, is we would say there's a marginal benefit function for oil, and let's say it's 10 minus 0.5 Q, and we would say there's a marginal cost of extraction. And in this case, we don't assume, and perhaps this is a bad assumption, but we don't assume that it gets any harder to extract as we supply more oil. We just assume that this pump keeps pumping and it's a constant marginal cost. So it's a marginal cost of extraction of 3. So we view this as our demand, and we view this supply to be the extraction cost. And I could say per barrel. All right, so we know that before the midterm, what do? We just set the marginal benefit equal to marginal cost, and that tells us how much oil we're going to supply. So if we set marginal benefit equal to marginal cost, that gives us the solution that 10 minus 0.5 Q star is equal to 3. And so I'm going to bring the 3 over, making the 10 into a 7, bringing the 0.5 Q over to the other side. So that tells me that 7 is equal to 0.5 Q star, which means that Q star is equal to 14. So in the myopic case, if all I care about is my supply and my demand, my supply and my demand, in the myopic case, if the marginal benefit is 10 minus 0.5 Q and the marginal cost is 3, I set those two things equal to each other, and that says I should extract 14 units of oil from the ground and leave the rest, however much it is there, in the ground. And that's how much I'm going to sell. That's how much I'm going to turn into money. But the thing is, we'd say, but what if there is only 20 units total? So inside the reservoir, inside the ground, inside the oil well, we can only have 20 there. That is enough for us to get all of it out, all 14 out this year, and still have some left over. But the problem is that the next year, if I use the same decision making, I'm stuck. So if I'm going to just go to the next page here. So again, just as a reminder, the marginal benefit is 10 minus 0.5 Q. So the marginal cost is 3, and that tells me that the myopic Q star is equal to 14. You'd say, but if the total is equal to 20, then next year, so I'll say Q2, is going to be necessarily less than or equal to 6. So the next period, it'll be impossible for me to apply the same decision making. And moreover, so if I were to think about this marginal benefit and cost, I can say, well, in this year, I was able to set marginal benefit equal to marginal cost, and that gave me that Q star equal to 14, and that gave me a price, P star, equal to 10 minus 0.5 times 14, which is equal to 3. So the year 1 price is equal to 3. The year 1 marginal cost of extraction is also equal to 3, which tells me that the marginal net benefit is equal to 0. This is also referred to as the marginal user cost is equal to 0, or the scarcity rent is equal to 0. So I make no extra money on the oil that I sold this year. So we're saying if everybody out there is got myopic decision making in the oil industry, everybody out there myopic decision making in the oil industry, got that everyone out there. The competitive equilibrium is for us all to pump so much out that the market gets all 14 of these units, and we are going to sell them at cost, basically. We're going to sell them where the price is going to be equal to the cost it takes to get them out of the ground. And so we don't get to charge them any additional rent. So we don't have, so the rent is equal to 0. But because the total is equal to 20, the most that we can sell or extract in year 2 is 6. So you say, all right, we sold 14, we're going to sell 6 next year. May as well just sell 6 next year. I guess it's the best we can do. So then you have to ask yourself, what's the price of that going to be? We know what the marginal benefit is. We know the demand function. So what is the price in year 2? Well, the price in year 2 is the marginal benefit function evaluated at 6, which is just equal to 10 minus 0.5 times 6. Well, half of 6 is equal to 3, so this is equal to 7. So the price in year 2 is equal to 7. And notice that the marginal cost is still equal to 3. So now the scarcity rent is equal to 7 minus 3 is equal to 4. So because I only had 4 to sell, by selling them all, I actually sell them at a higher price. So competitively speaking, because the market only has access to 4 of these things, my competitors cannot underbid me. The best we can all do is to charge 7. So these are dollars per unit. And these here are dollars per unit, which means all of us get the benefit of making a scarcity rent of $4 per unit. All right, so I've said that's for the competitive market. You know, now let's say there's a bunch of oil suppliers out there and you're one of them. You look at this and you say, you look at this in year 1 and you're just doing the math ahead of time. And you said, you know what? My competitors are selling things at such a lower price that's making me want to pump out as much oil as possible just for me to make any money whatsoever, because I have to sell my oil at a lower price. So in order for me to make money, I have to sell more oil. But then I look at this and I say, but next year I will be able to sell my oil at $7 per unit. I'm selling it right now at $3 per unit, right? So this is the this right here. This is the price is $3 per unit, and that's the year 1 price. I'm just emphasizing that. And I look at this and I say, next year I sell it at $7 per unit. So for me, as in the competitive market, it tells me, what if I hold off on some of the barrels here? I'm not gonna extract quite as many barrels, even though my competitors, they're going hog wild and they are extracting all the way up to provide the market with these 14 units. I am going to hold off a little bit so that I have some oil left over, so that next year I can sell it at a higher price. Now, if I'm thinking that, the rest of the market is probably also thinking it. So all of my smart competitors have also done the math. And so they then start realizing that they can stop extracting as much and start selling it next year. And so overall, what happens with the competitive pressure is people shift their allocations to extracting next year. And as they do so, it undersupplies the market this year. And that causes this year's price to rise. And it starts getting closer to fully supplying the market next year, which causes next year's price to fall. And so that's what we're focusing on here, is what the competitive equilibrium will be when this is the case, as people start shifting, is that because they can't supply 14 each year. So because they can't supply 14 each year, the little bit they can supply next year creates an incentive to actually put more oil into next year. And that another way to view it is there's an opportunity cost to selling oil this year, because you can make more money on that oil next year. And so the scarcity rent that you will eventually be paying, or that your customers will be paying this year, is paying you for the opportunity cost that is lost by selling you oil this year and not next year when it's going to be a higher price. So what we're going to see here is this Hotelling's rule thing is just accounting for the externality of being able to sell oil next year at a higher price. And so, and because I can sell oil higher at an extra price next, or a higher price next year, then I can charge actually a higher price this year, because someone needs to compensate me for the opportunity cost lost of selling them oil this year when I can sell it for more expensive next year. So that's kind of the magic of what's going on here. So let's, so the big thing here is that we need a way to figure out the allocation across both time periods simultaneously. All right, so how do we do that? All right, so any questions about that so far? Is it clear why the price would be higher in year 2? And then key terms so far is rent or scarcity rent, which is also known as marginal user cost. And this is the price minus marginal cost. All right, so how do we solve this problem? Well, if we go back and we think about how do we solve it for the 1 period case, then you can remember that, you know, we've got these I'm deciding how much detail I want to give here. So we've become familiar with, for the 1 period case, I'll write it over here. So this is the myopic, or I can say unconstrained case, or unlimited case. Then we know that we just draw these market diagrams where we drew a demand function, and we also drew a supply function. And so I guess I can write those just to remind us: supply, which is marginal cost in the ideal case, and demand, which is marginal benefit in the ideal case. And so the market equilibrium occurs where these things intersect, and that gives us our Q star. And the net benefit, the net total benefit, is the area between the curves. So if I were to highlight the area between the curves here, this is the net benefit. And back, you know, we would often say this is consumer surplus plus producer surplus, is the area between these curves. All right, so was the old way of viewing it. And we viewed it that way because we often had supply and demand curves. And so this was a convenient way of us seeing what was going on by plotting them on top of each other. Now, an alternative we could have done is actually plot the marginal net benefit. So if you remember the supply curve, marginal cost curve, we can view the marginal cost as kind of the derivative with respect to quantity of the cost curve. And we can view marginal benefit as the derivative with respect to quantity of the benefit curve. Now, we could instead define a marginal benefit or a net benefit. So we can say, you know, if we just focus on net benefits, and then that then allows us to define a marginal net benefit, which is equal to, and the net benefit is just benefit minus cost. And so the derivative of benefit minus cost is just going to be marginal benefit minus marginal cost. So we can basically take the difference between the blue line and the red line above. We can take, you know, we can plot each one of these differences out, and we get another line, a single line. So that's what I'm doing here is maybe I'll move this down, and then I will redraw the axis here. And so we still have dollars per Q and Q, but now when we plot the marginal net benefit, we just have a single line, and that line is going to start high, and it's going to end at 0, kind of in the middle here, where we had the intersection before. So before, our Q star was, I think, about here. And so our marginal net benefit curve is going to connect those two. And it goes on down beneath there. So I can, you know, if I wanted to, I could keep drawing it going further down. But at that point, you know, you end up getting negative benefit. The costs end up outweighing the benefits. And the area between these two, or the area under this curve, that area right there is equal to the net benefit, just like the area above. So this here is the net benefit. Now, the downside of drawing it this way is it's hard for me to graphically see where the consumer surplus is and the producer surplus is. But if I'm not focused on that problem of understanding how benefits are allocated from producers to consumers, if I'm just interested in all of society whatsoever, I don't really care that much about how the benefit is chopped up. But what I am interested in is that the area here is equal to the area up there. It's just been shifted around a bit. So in this framework, rather than looking where the marginal benefit curve crosses the marginal cost curve, we look for where the marginal net benefit crosses 0. So the efficient condition here, so up here, the efficient condition was where marginal benefit is equal to marginal cost. Down here, the efficient condition is where marginal net benefit is equal to 0. And that you can actually view that as equivalently saying where the marginal user cost is equal to 0. Because if you think about it, the marginal net benefit, maybe I'm getting ahead of myself. So for now, I'll just say where marginal net benefit is equal to 0. That is an alternative way to do the 1-period case. So, and I see a so far so good in the chat. I don't know where that came. I'm sorry I didn't see it earlier, but I'm glad to hear
I
that.
got a question.
Yeah, go ahead. Sure.
So, you might have explained it before already, but I was lost for a second. So what's the point of having the second graph?
Well, we're getting to that. So,
okay.
For the 1-period case, it doesn't help, but it does help us for the 2-period case.
Okay.
All right. So, so that's a great question. But what I want you to take from this is that the area under, and I will write that. I can write that in a separate color, maybe green. So the area under the marginal net benefit curve is benefit to this period. So if you want to maximize that area, then you take the area all the way to the point where the marginal net benefit is equal to 0, and that maximizes the triangular area here. If you stop early, then you leave some of that area on the table. So then that way the area is only this one. So then you leave that ends up being your deadweight loss. So this is the no deadweight loss condition right here, because that's the efficient condition. We've gone all the way to the efficient condition. All right, so for the 2-period case, we have to think about our intertemporal social welfare. And what we use for our intertemporal social welfare is the so-called net present value. So we want to maximize net present value, otherwise known as NPV. And your net present value is defined as the your present value plus a discounted form of your future value. And I'm only worried about one period, so I'm not going to worry about the exponent t. So, so this is the direct benefits from period 1. Those there are the direct benefits to period 2. And so then this grouping here, those are the indirect benefits in period 1 from period 2. That whole thing there, where, by the way, R is our interest or discount rate. And so in the previous lectures, I would sometimes refer to that quantity 1 over 1 plus R as beta. So I can define beta as 1 over 1 plus R. And normally I would have a t up here, but I'm taking t is equal to 1. So it's just equal to 1 over 1 plus R for the 2-period case. And so this is the marginal rate of substitution with the future. Okay, so that's what it is in the abstract. So what it is concretely for this oil problem. Well, for the oil problem, it's the net benefit of, we want to maximize the net benefit from, I'll say Q1 and Q2, where Q1 plus Q2 is equal to the total amount of oil. So Q1 is how much we take out in year 1, Q2 is how much we take out in year 2. And so that is going to be equal, so sorry, I didn't mean right, I meant to maximize the net present value which is equal to the net benefit applied to Q1 plus beta times the net benefit applied to Q2, where Q2 is just equal to T minus Q1, where T is our total unit of the resource. And so I could say this is the total resource. And so it's the same net benefit function, but it's discounted because they're future rewards, and that's what beta is doing there. So I'm maximizing my direct rewards and my indirect rewards together. And so what does that look like in the new plot that we just had here? Well, we already had, if we take our plot here, if we plot the marginal net benefit in period 1 on this axis, and then for kicks, I'm going to add a second axis out here. Maybe I should draw it straight. And so I'm going to place a second axis that I'm going to refer to as marginal net benefit. I'm going to refer to as beta marginal net benefit Q2, which is equal to beta marginal net benefit T minus Q1, because this is just equal to Q2 out here. So I've just
Can you go
plotted.
back 1 second?
Yeah. Sorry about that, Ross.
All right, thank you.
So I've just taken the discounted future rewards and I'm going to put them on a vertical axis right smack at where T is on my marginal net benefits from year 1. And why do I do that? It's because I know that I've effectively got for Q1, I know that I've got this axis that climbs from 0 to T. But once I make my Q1 decision, I fix my Q2 decision. So this axis is effectively also defining an axis that goes backwards from T down to 0. And so if I were to choose to extract all T units of oil in year 1, so Q1, if I were to take it all the way equal to T, then that necessarily means I have no units of oil to extract in year 2. Or if I were to choose to extract this much oil in year 1, then that means I would get this much. So if I extract this much oil here in year 1, I get this much oil down here in year 2. I get whatever's left over. So this method of plotting these two axes where the marginal net benefits from Q are going to go this way and the marginal net benefits from Q1 are going to go this way allows me to put them both on top of each other. And so so what I plot here is I will plot, this is my, this point up here, you could view this as the marginal net benefit curve, or this is equal to the marginal benefit at 0 minus the marginal cost at 0. I guess I should clean that up. So this here is just the marginal benefit at 0 minus the marginal cost at 0. And that thing is going to go down to, let's say it's going to hit here. So I'll draw a line connecting those two. And then on the other side, I discount whatever that is by beta. So let's say, for example, if if R is equal to 0.15, do 1.5. I'll say 0.25. Then beta is equal to 1 over 1.25. which is equal to 0.8. And so that means that this over here, this will be at 80% of whatever the marginal net benefit at 0 will be. And then that will then end here, which I basically have taken the same distance here and I've put it over here. So this point over here would represent the point where we decide to extract, it's like the myopic case for year 2. So if we just tried to do all of that just in year 2 and only, whatever we got left over for year 1, that would be this tiny amount here. And that would be that one there. So if I connect those two with a line, then these two curves together, so this is beta marginal net benefit of Q2, and this is marginal net benefit of Q1, then this gives me a way of adding up the marginal benefits for the 2 periods graphically. So the idea here is if I were to say choose, let's say right here, if I were to choose to take out, well, maybe let's go with the myopic case. So let's say I choose the myopic case over here. So let's say that I choose that I want to extract this much oil at Q1. Well, what that tells me is that I am going to get the entire triangle of benefit directly from period 1, just like on the previous graph or the previous page, or 2 pages, I guess. But then how much benefit is going to be left over for period 2 for me to get indirect benefits on? It's this funny trapezoid area. Maybe I'll use a different color that's a little clearer to see. So the net present value is equal to the sum of the 2 areas. And so this here is the net benefit, period 1, and this is the discounted net benefit from period 2. So I can maybe draw little lines to indicate that this is an area and this is an area. And so the net present value is just equal to the net benefit 1 plus beta net benefit 2. And what I hope you can see here is that there's obvious deadweight loss, that there is this section right here in the middle that maybe I could highlight with a different color, maybe a light gray. And so this region in the middle here is the deadweight loss. So in other words, if I want to maximize net present value, I would like to get rid of the deadweight loss. We say, well, how do you get rid of deadweight loss? Well, in this case, to maximize net present value, that suggests to me that I should be right here. Because if I were to extract this much from year 1, and however much corresponds to that from year 2, then what that's going to do is it's going to take some of the direct benefit away from year 1, but the discounted indirect benefit from year 2 will be larger than the benefit that is being taken away from year 1, so that overall what I get is more net present value. Because as you're seeing, if I move this backwards, this area is going to disappear, but this area is going to encroach on it and pick it all back up. And so this point right here is got to be the optimal point.
If you do the optimal point, that would get rid of the deadweight loss, right? There'd be no deadweight loss at all. Okay.
That's right, exactly. And that's sort of our goal. So if I were to draw a line down through here, then I'd say that this, whatever this Q1 is, and the course, which would be, right here, and whatever the Q2 star is, which would be right there, which is just T minus Q1 star, then I can say this strategy eliminates deadweight loss, and that maximizes net present value right there. And that, I guess I should clarify, this is deadweight loss at that strategy. All right, so that's the graphical derivation. We can do all this with calculus, but I've just tried to do it all with graphs, is that if you buy that the area under the marginal net benefit curve is the net benefit, then I'm hoping graphically you can see here that this graph shows that the efficient condition here is where the marginal net benefit from period 1 is equal to beta times the marginal net benefit for T minus Q1 star, where this is equal to Q2 star. And maybe I'll write that in cleaner. And so I will highlight that condition as being an important one. So that there is our intertemporal equimarginal principle. And so that is like marginal benefit equal marginal cost, but we've generalized it to be intertemporal. If beta is equal to 0, that means you do not care at all about future rewards. You're in the myopic case. When beta is equal to 0, this just turns into marginal net benefit is equal to 0, which means you're back to marginal cost is equal to marginal benefits. So we now generalize marginal cost is equal to marginal benefit to apply it to multiple periods of time. And that's what we're saying right there. And it's justified by this kind of graph right here. And so using that, we can now write some equations that allow us to solve for the optimal amount of oil we need to extract this year versus next year. Are there questions about that?
So if beta changes, then the slope of that blue line would change, and then the Q star would also change. But it's the same kind of math where we're looking for that intersection point, right? That's
right. It's an excellent point. Is that this graph helps us reason through what would happen for those things. So, as an example, if maybe I'll draw this on a fresh page here, but if I were to just generally draw that shape, so just going to draw this kind of U-shaped axis. And so I'm just redrawing the same shape from before, where this is beta marginal net benefit T minus Q1, and this is marginal net benefit Q1. And so if I were to pick a point, draw this down, and then another point that would be lower than that, and then it's going to intersect at the same point here to match the other one. And so this is beta. And so if this axis has got 0 here and T here, and this is Q1, And then you could view Q2 if it helps as T here and 0 here. So Q1 increases that way, Q2 this way. Then we can start asking what if questions about this model. And so one of the things we can say is, and then, as a reminder, beta is equal to 1 over 1 plus R, where R is our discount rate. And so you could say that what if we discounted the future more? So, if you discount the future more, so then increasing the discount rate R is going to decrease beta. Decreasing beta, so if I were to decrease beta, this point over here is always going to stay fixed, but the line is going to rotate down if you decrease beta. So this is decrease beta. So remember that increase R implies decrease beta. Now we know that our optimal point is right here. So that's the optimal Q1 star. So if we decrease beta, I hope you can see that the net result will be that this intersection point moves down and we will extract more from the current period. Or if you go the other way, you could say, well, what if we increase beta? So if you increase beta, so that would be a decrease in the discount rate. Decreasing R is an increase in beta. So if I now increase beta because I care more about the future, that will rotate this line up. Again, this point stays fixed, but this goes up, so the line rotates up. So this point moves up the graph, and we start extracting less from the current period to give more to the future period. We can also do a similar game for T. And so we can say, like, well, okay, if I were to decrease T or increase T, well, that's effectively the same thing as taking this second axis over here. So maybe I could highlight that in a red shade. And so if I were to increase T, then again, the point at which, well, it gets a little more interesting because both lines end up changing. Because if I, well, no, actually it doesn't. It doesn't. I take that back. If I were to increase T this way, then this line stays fixed, but this line ends up being shifted over to follow the axis. And so that whole line will end up moving, so that if I increase T and that line moves over, then that is going to cause this point to move down. So increasing the amount of resource available makes me more and more myopic. So it allows me to extract more and more from the current year. On the flip side, regardless of what my beta is set to, if I decrease T, so if I make things more scarce, then it is going to shift this whole line over. And so as it shifts this line over, then it's going to move this point up, meaning that I'm going to extract less from the current period. So this actually gives you a way to play with the price path over time, because you can see that as you get less and less of the resource, it's like drawing this 2-period graph over and over and over again, where your next period has got its second axis shifted to be in a different spot. And as you keep moving them farther and farther over, it will cause this intersection point to move up and up and up, and it'll cause the prices to move up with it.
I got a question.
Yep.
So this might be this is like a bit of a weird question. So for this entire principle, is it possible that a deadweight loss might occur in the first net benefit, the left side, or does it only occur on the second or on beta net benefit?
It is, and if you look at the notes that I put available, my notes that I put available on the main Canvas site, I show both of those cases. And if you were to undersupply the current market, So if you were to say this is the efficient, but if I were to set it over here, then what I'm actually doing is putting too many benefits into the future and not enough in the present. So you end up getting a deadweight loss on the
Okay,
left-hand
so it is
side.
possible then if you do too much in the
Yep,
future. Okay.
right. This little bow tie is where the deadweight loss can live.
Okay.
All right. Yeah, okay, so with that, I mentioned price path. Then the last thing that I want to kind of cover here, and if we have time, I can work a specific example, because you will do this on your homework. But if we recall that in both periods, the price is equal to the marginal benefit of the quantity that is extracted, and the cost is equal to the marginal cost of the quantity extracted. And so the scarcity rent, which is otherwise known as the marginal user cost, MUC, is equal to just the price minus the cost, which by the equations above is just the marginal benefit minus the marginal cost, which is just the marginal net benefit. And so if I were to take this point over, then this distance here, this point on the y-axis, we can view that as the marginal net benefit at Q1 star, but that happens to also be equal to the marginal user cost, or the scarcity rent. And so this diagram also shows us how much profit we're making off of scarcity. If we have no scarcity whatsoever, then that moves this point all the way down to the axis so that the marginal net benefit's equal to 0, and thus the marginal user cost and scarcity rent's equal to 0. So this distance right here is just a graphical depiction of that scarcity rent. And as I was mentioning, as you get more and more scarce, what you're doing is shifting this blue line over more and more, which is causing this purple intersection to move up higher and higher. And so that's one of the reasons why graphically we see that the scarcity rent increases over time, is that as the resource is becoming less available, then we charge more for it. And that is going to cause the marginal user cost from year to year to year to go up. So the price path is going to go up, and it's going to bring the margin, even because the cost stays constant and the price is increasing, then the scarcity rent is increasing over time as well. And so that's basically the Hotelling's rule, is just rephrasing our 2-period condition for the multi-period case. So the Hotelling's rule basically is saying that the marginal user cost in any following period, so marginal cost 2, is going to be equal to 1 plus the discount rate of the marginal user cost in any previous period. So this is our previous period, and this is the next period. And this this is related to the price path over time, is such that, and for the 2-period case, this is identical to the intertemporal equimarginal principle. Which is just the marginal net benefit in the current period, Q1, is equal to 1 over 1 plus R, which is beta, times the marginal net benefit in the next period. So if you rearrange that, you put the 1 plus R on the other side, then what you see is that this thing is basically the marginal user cost in the next period, and this thing is the marginal user cost in this period. And so Telling's rule is saying if the market is operating efficiently, then this will happen just naturally due to competitive pressures. People will realize that they can get more money out of future extraction than they can from putting things in the bank. So this is basically that you manage natural resources to match returns from the bank. And so in that example I gave earlier, if you do the myopic case, you get no scarcity rent now, so you have nothing to put in the bank. And then magically, the oil well gives you scarcity rent, huge amounts of scarcity rent in the next year. And so you then, if you think of the oil well as a bank, you'd say that, wow, the oil well is a much better interest rate than my bank. I better put my money into the oil well bank. And the way you do that is you decide to extract less this year. So every extraction means selling it and then putting that money into the bank. And so if you extract less, you have less money to put in the bank, but that unextracted oil actually earns interest underground because oil becomes more scarce, and more scarce resources you charge more for later. So what this is telling us here is that low interest rates encourage conservation.
Interest rates are the same as R, right? Just making sure.
Right.
Okay.
That's kind of Hotelling's insight. That we would expect that if everybody is doing things efficiently, they should be getting returns from their natural resource investments that match their bank returns. Okay. So, so with that, in the last couple of minutes, I can just set up a quick example of how you would solve a problem like this, like you would have on your homework. So if maybe I'll use, there's an example in your book that's already been done, so I will use maybe a separate example, and I won't draw out all the curves just so I can get the math down. So if we assume, so this is just example. For 2-period case. And so if we say, well, what if our marginal benefit is equal to 4 minus 0.5Q, and our marginal cost is equal to 0.3Q, then we can combine these together, and we can say the marginal net benefit is equal to the marginal benefit minus the marginal cost, which will be equal to 4 minus 0.8Q. And then so if I then say, well, then I'm going to give you an interest rate R equal to, we'll do 100%. So the interest rate equal to 1, so that's 100% interest. You could view this also as 100% discount rate. We discount future rewards by 100%, so then our beta is equal to 1 over 1 plus 1, which is equal to 1/2, or 0.5. So how do we solve for the optimal amount of extraction? Well, we end up just setting the marginal net benefit, which is this thing up here. We're going to set marginal net benefit Q1. Oh, and I meant to say also there's a total supply available of 6. So that's total available. So we set our marginal net benefit in the current period equal to beta times marginal net benefit of what's left over for the second period. And I can just plug in numbers there. So I can say, well, that's 4 minus 0.8. I'll put little stars here. 0.8 Q1 star is equal to 0.5 times, and then the same expression, 4 minus 0.8, but now I have to put in this 6 minus Q1 star. And then I solve for Q1. And you have to do a bunch of arithmetic, but if you do all of that arithmetic, what you should end up finding is that Q1 star is going to be equal to 3.67. And then that must imply that Q2 star is equal to 2.33. So solve. And then you get that. And then the other questions that I'd ask you then is, all right, so what's the marginal user cost? Well, then I'd have to figure out the price of that. So you can solve for the price in both time periods, and they're just equal to the marginal benefit at that Q. And so the marginal benefit at that Q is going to be equal to 2.165. And again, I just plug that in to the marginal benefit up here. So I guess I could write that underneath there. That's just equal to 4 minus 0.5 Q1 star. And the price in the second time period is equal to 2.835. And so we notice that the price did increase as expected over time. So in that case, I can then calculate the marginal user cost for both of those. And so in that case, I just subtract off the marginal cost of extraction, which the marginal cost of extraction is up here. And so the marginal user cost in period 1 is just equal to 1.11. This is just equal to P1 star minus the marginal cost. And the marginal user cost in period 2 is equal to, oh no, I'm sorry, I screwed that up. I was misreading my notes. I jumped a step there. So the rest of this example, I don't want to hold you guys too much longer, but the rest of this example is in the notes page. And so the next steps basically are to solve for the marginal cost in period 1, which is just marginal cost evaluated at Q1 star, and the marginal cost in period 2, which is just marginal cost at Q2 star. And then with those, you can solve for MUC1, which is just the price in the minus the marginal cost, and MUC2, which is just the price minus the marginal cost. And then if you then do the calculation, MUC2 minus MUC1 over MUC1, you'll find that you get exactly the discount rate out, where that in this problem is equal to 1. So those numbers are in the notes that are posted online. So I don't want to keep you too much longer, so I won't go and do them. But if you work those out, then that ends up being the outline of how you would solve this problem. And you'll solve a problem very, very similar to that on the homework. And there is another problem almost identical to that in the textbook where they use different numbers. So with that, I don't have an attendance question for you because it's voting day. If you can vote, I encourage you to vote. Otherwise, if you have any questions, I can stick around for a few minutes, but that's all I've got for you.
I just got one more question that's regarding the final exam.
Uh-huh.
So basically there are 2 parts of the final exam that you said. Like one part's gonna be the 80%, which is gonna be the lockdown browser, 90 minutes of what we learned so far. Is that gonna be cumulative, or that's gonna be what we learned Like with
The
New Year's
final
version?
exam is, yeah, so the final exam is cumulative
Okay.
over the whole semester. So that's all units.
And you said
And
that one, we're
your,
gonna be having a review session for that one?
yeah, and there will be a review session. Yep.
Got it.
And your score is basically going to be, 80% of test 1, and then 20% for test 2, where these here are identical tests, but test 1 is under lockdown browser with 90 minutes, and test 2 is open book and classmates with 24 hours. And so this is Thursday and this is Friday. And the review session is Tuesday.
And those are all that last week of like the November 30th, December 1st, December 3rd. Well, I guess 3rd
Right.
and 4th. Okay.
Yeah, so this is
And so-
before, go ahead.
Okay, and so the benefit of this structure is that we get to clarify any of the things that we think we missed on Thursday and maybe get some points back for that, but we're taking the same test twice.
Right, and no solution set is between them.
Okay.
So the idea is you get 80% blind, and you go into it and you take that, and then you don't get a solution set after that. You will after the second test, but after the first test, you don't get a solution set. So then between then, you can say, wow, that problem 6 was really hard. I didn't quite understand that. So then you can go back and hopefully help each other. And feel free to use Slack or whatever else. And then try to then learn from the first test and then practice what you learned on the second test.
Okay, interesting. Thank you so much.
Mm-hmm.
Thank you, Professor.
Yep. All right, I think that's it. Have a good day.